Hello again, folks. Today we're going to be covering Chapter 6, so we'll be covering primarily 6.1 and 6.3 with reference to 6.2 and 6.4. Okay. Here's a quick view of the calendar. Okay, this video is for Wednesday, June 8th. So we'll be covering 6.1 through 6.4 per the schedule. The packet is quite hefty because it's those 4 sections. This is the completed overview for the course, really. To this point, I have been trying to obscure this half that is in blue because we were discussing algebraic functions, but it seemed appropriate now to show you the whole thing. To summarize, we're in transcendental function territory now. Which for us immediately would be exponential and logarithmic functions. Okay, these are inverses. I want to point out some things on the sheet and move from there. I also, from the diagram that I stole from the textbook, the overview of graphs, I took the blinders off and included these 2 graphs. Right, for base E and naturally logarithmic functions. Right? Any exponential and logarithmic function doesn't have to be base E and natural log per se. Will basically emulate this shape. Right? And what's very interesting here is just like the other graphs, to pay attention to, if they don't go through the origin, they might at least go through 1, 1 or -1, -1, something like that. All right, so it's good to pay attention to this for the sake of comparison. Here's a table that I have for generating coordinates so that you could see how it works. Some graph paper as always. This is basically the diagram that I have made for the graphs of exponential growth and exponential decay. All right. I'll go into detail. There's some word problems to walk you through that. This is a diagram I made of to summarize the numbers that we deal with. Primarily we're dealing with real numbers, of course, but in theory, especially if you go into calculus, you might see imaginary numbers. We're going to be introducing E today, so it seemed appropriate. Here's something of a worksheet to explain where E comes from and the graph that it would produce. These are applications I tried to summarize. Different incarnations of an exponential function. It has little extra features, which I've tried to describe here, based upon whether you're examining population or compounded interest, or the mass of something radioactive, perhaps, or continuous growth or decay. Now the word problem. This is the part of section 6.2 and 6.4 that seem to be relevant. I figured, okay, what better way to summarize it than these 2 tables that are right from the textbook resource, right? I thought that was pretty nice and concise. All right, these are different versions of the transformation model pertaining to each, the exponential version and the logarithmic. And this is a sheet I made again, how to convert from logarithmic form to exponential form and vice versa, and when you're evaluating. Lastly, these are 2 special types of logarithmic functions, base 10 and base E. There's an infinite number of bases because there's an infinite number of numbers really, but these are special, all right, and a reference to the change of base formula. Okay, all right, so if you're following along, do print that out. You can annotate as we discuss. All right, I'll put this aside to keep that trouble. And I think I have rearranged my furniture, so I'm going to probably have to readjust my camera here. Bear with me. I'll close that door back here. Definitely too low. Alright. Scoot it on over. That's not so bad. Where are the glasses? That looks reasonably clear. I would love to make it as sharp as possible. I think that's probably as good as it's going to get. Alright. Here, as I mentioned, is the overview that I've been working on. Well, they could always be improved, but we had to this point been discussing algebraic functions the first half of the course. Get that wind out of the way here. Last thing we were talking about was rational, which are basically polynomial functions on top of polynomial functions. Right now we're shifting focus over to, which is really approaching calculus, the transcendental functions. Right? Specifically, your attention should be here and here. Right? The exponential and logarithmic type. Right? Key point to this is that these are inverses of each other, all right? Which means that they are something that you could convert to another by a process. All right? What you notice traditionally we have when we talk about functions, right, is that if we're not using function notation f of x, you see we could call it y instead. Let me zoom in on this feature. All right, take a look over here. Since they are inverses, all right, instead of calling it function of x equals b to the x, notice what the degree is. The degree is where the actual variable input is. All right. If this is truly an inverse, then what would happen would be the position of the variables x and y would shift, and they do. It's just that they're not normally presented that way. Right? You could very well write a logarithmic function x equals, right, b to the y instead of y equals b to the x. All right. What is written often is something like this. The version of it that is expressed from the perspective of y. So y equals log, in reference to a logarithm, of base b of x. Okay. Then there are these other references down here we're going to get into later. The common log is the base 10, and the natural log is base e. All right, but for right now, let's go through these things. All right. Let me show you the graphs again up close. Here is what I swiped from your textbook, because I think it's very nice. Not that I stole it, but I think it's a nice summary of the types of graphs that you should keep in the back of your head. They're tools, right? Tools in the toolbox. Linear, the most basic type of which is the identity. Square is the most basic type of quadratic. Square root, cubic, the staying alive, as I like to call it, the cube root. Reciprocal is just what we were getting through, which is the most basic type of rational function, absolute value, the V shape, and now these two. Again, if you zoom in on features here, they also include the domain in interval notation and the ranges. Okay, there's any version of exponential is basically going to be a curve like this, and in theory, if they don't go through 0, 1, all right, the y-intercept at this point here, and in the case of logarithmic, remember the x's and y values switch 1, 0, it would be due to a coefficient up in the front. All right, remember, almost anything, almost any base to the 0th power would be 1. All right, almost anything. So if you had a coefficient that was in the front here, it would just scoot you up a little bit further up the y-axis, all right, or down further, depending upon what the the coefficient actually is. All right. Now to get your feet wet, for exponential functions in general, let's see how they behave by using some test points. That is to say, let's generate some dots. There's a table to this effect. All right, and then we could plot these. Remember, the old method, the most basic method of graphing, the most brute force method, all right, is to generate your own coordinates. That works for virtually everything. That's time consuming, and it's not always, for that reason, the most efficient way to go about the process. But if you really want to get a feel for something, I would do that. All right. So, using a calculator is great, of course, but you know, it sometimes robs you of the experience of, you know, really getting in with intimately with the function. So, let's say that you had this, a very basic type of exponential function. I'll use a more plain base, 2 to the x, so base 2. All right. If I decided randomly, just for the sake of convenience, to use these inputs, -3, -2, -1, and it is ideal to use small numbers because they're warm, fuzzy, and familiar. They won't scare you too much. All right, and systematically put them in the function. In this case, that means that you're going to be putting them as an exponent rather than as a base number, what would be the normal situation. So, just to write it in a more plain way, this particular function, y 2 to the x, you might write several times. And this is maybe overkill, but I'm just doing it this one time, this one occasion. You then will put a -3 in here, a -2 in here, a -1, a 0, a 1, and a 2. Right? A couple of things to remember from rules of exponents, the kind of thing that you would see in an Algebra 2 class. Right? When you have a negative exponent, what that produces ultimately is something that looks like a fraction. So essentially, in this first instance, you would end up with 1 over 2 to the third. Right? And in the second one, you would get 1 over 2 squared. Right? And then again, another negative, it would be 1 over 2 to the first. And then you could do the perform the actual operation of the exponent. In this case, 1 over 2 to the third would produce the output of 1/8, right? Which means you'd have a dot at the location of -3, 1/8. That's a little difficult to graph, being that it is a fraction and it's rather minuscule one at that, but it's not impossible. All right. In this case, you'd have 1 over 2 squared would be 1/4 rather. All right. So here again, inching up a little bit, you'd have at -2, 1/4. So from, what is it, 0.125 to 0.25. Then 1 over 2 to the first is just simply 1/2. 2 to the 0 is just 1. 2 to the first is just 2. And 2 squared is just 4. All right, which means that to round it off here, you'd have at -1, you'd go up to 0.5, halfway. At 0, you'd be at the y-intercept of 1, which is more or less the normal situation. And then at 1, you'd be at 2, and at 2, you'd be at 4. All right, I'm going to try not to erase those, and I'll show you how these are plotted, because it's kind of neat. Clear up a little gobbledygook here. And then proceed to graph these. So I'll stick with red here because it seems to show up fairly well. All right, at -3, 1, 2, 3, you would be just above the axis, right? At -2, you'd be a little bit further. up, but not quite halfway. At -1, you would be exactly halfway. At 0, you'd be up 1. And at 1, you'd be up 2. And at 2, you'd be up 4. 2, 4. And you can see, especially if, since there's a pattern forming here, there's this sharp curve upward. Right? And that will trend like so. Virtually all exponential functions behave that way. On the flip side here, the opposite side of this, all right, there's essentially a y-intercept, a y-asymptote, all right? This will approach y equals 0, but never reach it. Okay. What will happen is that these fractions will get infinitesimally smaller and smaller. Okay, so a horizontal asymptote essentially would exist at y equals 0. All right, as I mentioned, this is something that does not have a coefficient in front of it. All right. If it did, all that the effect it would have is that this would scoot up a little bit further at the y-intercept, or perhaps lower, if it, depending on what number's there. Okay. Now let me show you this. Here is a summary of exponential growth versus exponential decay. All right. And these two nice models to keep in mind. Exponential growth in the most basic incarnation of this would be just the base and then a positive x value, a positive x input. Let's see if this is just a little bit too bright. Okay, that's a little bit better, right? So do pay attention to that feature. We wouldn't bother writing a positive sign, but that's the difference between growth and decay, essentially. Do you have a positive exponent, or do you have, in this case, decay, a negative exponent? Right? That affects the graph in this way. All right? Essentially, it causes it to, instead of curve upward, to curve downward along the horizontal asymptote. All right. Now, as I said, typically the y-intercept would be 0, 1. Right? In both cases, whether it's decay or growth. But it also depends on the coefficient in front of the base. So a slightly amplified version of this, pun intended actually, is that you have an obvious coefficient sitting here, all right? And in the context of, say, some word problem, all right, the version of exponential growth and decay often incorporates that. All right, so think of the y-intercept as being 0 and then probably whatever the a is. All right? All right. The base number, that is what the exponent is actually affecting directly, is known as the growth factor. All right? But the a value here is the starting point. All right? All right. Let's do an example. Here are some word problems. We're just going to do the first one for right now. Is that visible? Good. Okay. This is an example of, maybe a little bit of light. This is to illustrate how to write a function, an exponential function, when the initial value is known, the starting value. Okay. In 2006, 80 deer were introduced into a wildlife refuge. All right. By 2012, the population had grown exponentially. Key phrase there, all right, to 180 deer. All right. Using this information and the appropriate model, this is the model. That's just a hyphen. That's not part of that's not part of the formula here. You're just using that. Write a function n of t. Just changing the labels. Right, number of dia over time. With time as the input, representing the population of dia over time t. Right, one will assume it's in years since they're talking about years. Right. Now, without moving it too much, because I want to sort of scribble out what's important. When you're reading word problems, a good habit is to circle the numbers involved here, because you're probably going to incorporate them somehow. All right. Dia over time is going to be years since 2006. Okay. Now, if this is the model that you're given, this might show up a little bit better in the dark. Y equals A times B to the X. Remember what I was saying before. A is the starting point. It's the initial value. All right. So what would you automatically substitute in here? The starting number of dia would be 80. Okay. The labeling is changing from Y to N of T instead. It's a function notation. And therefore, instead of X, this is changing to T. Right? Years since 2006. Right? So we have this much of it fleshed out. We can go further with it, and we'll plug in some more values. Now, we have one other number from here that we can insert in the function. The outcome, all right, after a certain amount of time has transpired. So if I substituted 6 years, right, because between 2012 and 2006 is 6 years. I could put a 6 here in place of time, all right? And at that point, there was 180 dia, so I could put 180 here. That means that I would have 180 equals 80 times b to the 6, all right? What I would do in this instance like this is then rearrange it to solve for b, because they really just want you to create a model that would work for any numbers, not just these particularly, all right? A general formula. But we have all the information we need. All right, so what I'll do is I'll move 80 over by algebra. All right, I hope that's visible. (180) divided by 80 is a shortcut. All right, you're gonna get a crappy number that is an improper fraction. Divide each of these by 2. That's 9, and that's 4. But leave it like that. All right, 9 over 4 would be equal to b to the 6th. All right. Now remember tricks from, I want to say it was chapter 2. All right. You could take the 6th root if you'd like, or the alternative rational style of the radical. All right. The opposite operation. Raise it here, raise it there for consistency. All right. So if you do that, to raise this to its reciprocal would be to the 1/6. Right? Remember, that's the radical that would technically be a 6th root. Right? With the 1 sitting here in whatever number. All right? The effect would be a number times its reciprocal would cancel naturally. That leaves you with b, which is what we're hoping for. And then you do the same thing to the opposite side for the sake of legality and balance and zen. All right? So you would have this raised to the 1/6 as well. Okay. So at that point, all right, just for the sake of space, I'll put this over here. You have b is equal to 9 over 4 to the 1/6, right? Being that it's going to be a 6th root, and that would make these rather cumbersome. You could use your calculator at this point. to see what the number would be, and then round it to a certain decimal. So in that event, there's a couple of different ways you can input this. Let me give you a little bit more light here. If you want, firstly, to write something in the style of a fraction, let me put this into parentheses first. Right? Hit Math, scroll over to Num, go down the list to n/d, assuming your software is up to date, and then enter 9/4. Not that, sorry. Scoot it over. Close the parentheses. Reading it backwards, sorry. There you go. And then raise it to, you could put it in a 6th root, but it would probably just be easier to put it in the rational style. In that event, I kind of like this other feature. M, again, down the list, enter it into the fractional form, rational style of the radical 6th root, and enter. And you see that you get this decimal, 1.14471 into infinity, it looks like. Round it to, say, 4 decimal places, all right? Which means you'd have something like this. Approximately 1.1447. Now, again, to answer the question as it was intended, right, use the information in the appropriate model to write a function representing population of n deer over time. That is to create a formula that would work for some situation beyond just these 6 years and these figures of 80 and 180. What I'm getting at is you craft this formula, right? Instead of saying y, you say n of t, right? You do use 80, all right, because it's the starting point, it's the coefficient, right, of 80, all right, times rather, and then you put in the b value that we just calculated. So we would write that in parentheses perhaps, 1.1447, and then raise it to a t, all right, instead of an x. Okay, and this will answer anything that is after the point of 2006. All right, it'll make the prediction of how many deer would be in the wildlife refuge. Right, 7 years after, 8 years after, 9 years after, whatever, based upon the initial conditions and this growth factor. Okay. Let me turn this projector off now because I don't need it. And lighten up the situation here. It's nice to have light, isn't it? Much nicer. Okay. Let's do a problem where you're writing an exponential function when the initial value is not known. Let's say that you're asked to write a function, something that passes through 2 points on the graph. -2, 6, and 2, 1. All right. Basically, there's a process to this. We're going to still be using this model, y equals a times b to the x. All right. Something with a starting point, a growth factor, and the input of x. I like y's and x's personally. All right. But because we don't have the initial value, namely the a, we have to find the a, and that's a little bit of a trick because it's going to be a couple of steps. All right. Essentially, what you'll be doing is, one, you're going to insert, substitute would be the more likely term, x and y, all right, and solve for a. All right, you're going to get an algebraic expression at that point. This will be an algebraic expression rather than an actual nice number, which is what we would really want. All right, that's ultimately what we're going to find, but there's some path in the way, a journey from here to there. Okay. Then you're going to insert a, this what you've gotten, into the model, namely that, with a different x and y. Right? Since you have 2 points, it doesn't really matter which one you use first, but let's say that you do it intuitively. We'll use x1, y1, meaning this number and this number at first to calculate a, and then when we plug it into the model again, we'll use x2 and y2. So this is the numbers 2 and 1. And then we will solve for b. Right. At that point, what we would get is an actual number. And then what you end up having to do again is substitute the b value to calculate a as an actual number. Okay. So I'm going to leave some of this for lack of space. I'll erase a little bit. All right. So erase that much. All right. And take my model here. I'll put it in green because it's easy to overwrite that. Because it's such a crappy marker. It's unfortunate. I like green. All right. Is that out of the frame? A wee bit. I wasn't about to do that. Sorry. There you go. Okay, here's our model, y equals a times b to the x. Again, we'll be looking for a, the starting point, because we don't have that initial value. So we'll take the little that we have. I'm going to call this one, just because it shows up first, x1 and y1, and put them here and here. So 6 on the y side, and -2 here. And then we will solve for a, right, which means that we're going to unfortunately get an algebraic expression rather than a number initially. Right? So if that were the case, remove this just for the sake of space. Beware, when you have a negative exponent, this is producing that expression instead, a reciprocal. All right? So what do you really have? You have 6 is equal to a times 1 over b squared. If you want to solve for a, you have to isolate a, which means that you're going to essentially move b squared from here to over there, right? If in theory, because it is now a denominator, in order to justify moving it from here to the opposite side, you would multiply by b squared for this cancellation effect, and then for the sake of balancing it, do it over here as well, all right? Which means that a is equal to 6b squared, right? An algebraic expression rather than a number, temporarily. All right. I'm now going to insert this value into the model again, but using the alternative x and y values. and we'll solve for b, and you'll get an actual number now. So here's the model again. Y is equal to a times b to the x. And I'll put in the numbers 2 and 1. A 1 here, very easy to work with. A 2 here, relatively easy to work with. And in place of a, this value that is 6b squared. And I have to clean it up just a little bit. You get, let's see, 1 is equal to 6 times b to the 4th. All right. Move the coefficient of 6 over the equals via opposite operations. So if it's being multiplied, it's pressed together. All right, that would require division here and there. All right, and therefore, b to the 4th would be equal to 1/6. All right, now you're going to pull the same trick as earlier from chapter 2, which is that you'll perform opposite operations to cancel here, and then do the same thing here for the sake of balancing. But since it's a square, it's an exponent of 4, it would be a 4th root as the opposite operation, but you could use the rational style of notation instead of the radical style of notation. So perhaps just write this simply as 4th to the 1/4, and then the same thing over here, like so. All right. The effect is that this is going to cancel, leaving you with b, so that you get an actual number, b equals something, and then plug that into your calculator, right? Because it's a rather cumbersome number again. All right, see what you get. You could put 1 divided by 6 in the / traditional way because it's more efficient. I personally love the to do it in the intuitive, rational style, but maybe this is just quicker, right? All right, and this is the figure that you get. 0.63894, rounded to say 4 decimal places. An actual number, a crummy number maybe because it's a decimal, but it's still correct. So this b value is about equal to 0.6389 approximately if you use 4 decimal places. All right. And now lastly, you're going to substitute the b value, insert it, whatever. All right, to calculate the a, an actual number. Now what you could do is you could either take the number that you've just arrived at, there's no sin in that really, or use the exact figure, which this would, if you have something in the rational style, even though it's cumbersome, it is actually the whole thing, right, not rounded. So you would get technically a more accurate answer, all right? Anyhow, you're going back here to the model. Sorry, I erased a little too much there. Of y equals a times b to the x. All right. And for sure, you're going to have this much, 0.6389, right? To calculate the a, we're going to have that sort of a formula that I erased, right? We had decided earlier, that a was equal to 6 times b squared, right? So now we can get an actual satisfying number, or some semblance of a satisfying number, by putting this b value in there as well, right? So if you put 0.6389 right, enter this into your calculator, right, you will calculate an A value. Right. So maybe being a little efficient, should square first, right, and then multiply by 6. If you already have this on your screen, the unrounded version of this, you might be able to get away with doing that first, right, and then multiplying by 6. Right, and there you have it. All right, that's correct for A. All right, 2.4495 rounded. Right. All right. So you have a rounded figure for A, you have a rounded figure for B. This would be sitting in here. To write it a little bit nicer, a little bit neater, let me put it down here. Y would be equal to the A value calculated, 2.4495, using the more exact figure that is not rounded for B. And then, just to fill in the void here, 0.6389 for the B value. This is A, this is B, and remembering that this is in fact squared. Oh, well, it's the X rather. All right, in the general form. All right. It was squared in the A incarnation of this. Okay. One more of these and then we'll sort of shift gears. Suppose you had to write a function from a graph. In this case, I'm just going to draw the picture very simply. Suppose you're given just this much of a graph, right, where you have a curving function like so, and these points, 0, 3, and then a second point, 2, 12. It's not to scale, unfortunately. It's not on graph paper. All right. Firstly, you would say, well, it appears to be exponential, right? It has that unique curve to it, right? And we're going to go through basically a similar process to last time, right? Right. In this case, we do know the starting point, though. So if this is the model that we're following, the exponential growth, it would seem to be, the function is equal to a times b to the x, right? And you could just substitute y for this. Right? We do in fact know the starting point, right? This is the a value here, right, on the y-intercept. The y-int is the starting point. The initial value known as a, right? So you would put a 3 in there immediately. Now if you want to calculate b, use some other point. In this case, you have a second point up here, 2 and 12, right? Just put the 12 in the appropriate place, and the 2 in the appropriate place. So, and then we could calculate what b is. Okay. So this is an x, this is a y. In place of y, we would put a 12. There's a 3 here from the starting point that we know. The b is what we're looking for, and the x value at 12 is 2. So it's b squared. All right, solve for b. Firstly, move the 3, which means that b squared is equal to 4. All right. Remember, it's a square function. It's being squared, so you could either use the fractional style of the exponent 1/2, or you could use intuitively a square root. The square root of this here will cancel, and you would have the square root of here. Now in theory it would be a positive or a negative. Let's go with the principal square root, which means that b is equal to 2. Okay. All right, and therefore the more cleaned up version of this would be the function of x. A value is still 3. We just calculated b is 2, and this is an x here. And you might say, oh, why don't you just combine 3 and 2? You can't, remember, because this base is affected by the exponent, but this coefficient is not, right? So they have to remain separate from one another in this arrangement. All right. Now let me show you something that's kind of neat. You could get your calculator to determine this for you. That is, you can get your calculator to help you write a function given the graph. As long as you recognize what the key features are and what type of function it is. If you know something is exponential is really what you must know. All right. Essentially, to get the TI 83 or 84 to produce the formula, all right, you must firstly recognize that this is exponential growth. All right. That's the prerequisite. This red is dying. And then create a list of ordered pairs. All right, in this case, what you'll do is there's a button on your calculator that looks like this. If you hit Stat, and then you just go over to Edit, what should be List 1 and List 2, assuming that they're empty, make List 1 your X's and make List 2 your Y's. Right. And then 2, press the Stat button again. Then scroll over to Calc. And then go down the list where it says exponential regression. Right. It'll give you the information. So just to walk you through that, here's a calculator. Clear. Make sure that I have this empty. Here's your calculator. If you press Stat, you turn it on first. Ding dong, come on. Hit Stat here, and the first option is Edit naturally. So these, if they're assuming they're empty, right? You could always just move the cursor up there and then press Clear and then Enter, and it will clear it out. Or you can go through Second and then Mem, which is the positive here, to clear all lists. Anyhow, you want this to be empty, and you, though it's not labeled as such, make List 1 your X's and List 2 your Y's. Okay. And then use the coordinates that you have. Now, in that last problem, it was 0, 3. So if this is x's, the first thing would be a 0, naturally. And then the second x would be a 2. And you'd have that much entered. Then you'd scroll over here and then pair it with the 3 for the y value and 12 for the 2 value. All right. There's not a lot of data here, but this will suffice based upon this much information. As long as you know it's exponential growth. All right. That's one judgment that you have to make yourself. All right. Stat. All right. And if you go over to calc, deep down this list here, there is exponential regression. It'll assume that you wanted the data from L1 and L2 unless you specify otherwise. Anyhow, there's the starting point. The A value is 3, and there's the growth factor B, right, which we determined was 2. Right? You would just insert these numbers in the model that you see above. A times B to the X. That's kind of cool, right? Now, let me turn on my projector again. Let's see what time it is. 3. Good. Let me show this diagram that I made a while back. Not that one. Okay. Somebody much smarter than me described these numbers that you see here as, that is to say, pi square root 2 E I, right? The superstars of math, which I always found that profoundly inspiring, right? Insightful. All right. They are, they're famous numbers, if you will, right? In the family tree of numbers, right? Now, in the instructions, a lot of times, especially when you're a little kid, it's kind of odd. The instructions, that even in 3rd grade, right? They'll say, find all real numbers or whatever. And I always hated that because I'm like, what do you mean the real numbers? Well, without anybody saying at the time, there is in fact another category, right? But the other category was too complicated to mention to a little kid. That means to me that don't bother calling something real numbers then unless you get to say that what it is, Anyhow, mostly what we deal with, of course, in practical math is real, all right? What is imaginary, though? The square root of a negative, all right? Why? Because you can conceive of the question, what are the identical factors that would make the radicand -1? You can conceive of that question, but there is no answer, right? There aren't identical factors that would make -1. They would be one positive thing and one negative thing. Those are not identical, all right? Anyhow, we don't throw it away. In upper level math, we just say, well, that's called I, all right? That's its own category. Everything else, it is real, all right? Of real, there are subcategories, right? There's rational and irrational. Again, I never found the instructions particularly enlightening. What does it mean to be rational? It means whether something is presented to you in the style of a fraction or not, it can be written as a fraction, all right? Integers, that is a negative and positive, whole number or a 0, can be written in the style of a fraction. How so? You put a 1 under them, right? Looks like a fraction, all right? Decimals that terminate, all right, like 0.3, can be written as a fraction, right? How so? The place value of the rightmost digit. So if this is 0.3, that's 3/10, right? So the tenths, THS, all right, is the denominator, all right? If you had something like a repeater, if it has a pattern to it, all right, there's an algebraic process, a technique for producing the fractional equivalent, all right? It ends up, in this case, being 3/9 to start with, and then it reduces to 1/3 would be better, right? All right. Then there's the other category. If things exist that can be a fraction, there are things that can't be a fraction. Those are the superstars, right? Those are the cool numbers, right? They would seem to be important to the universe, all right?
Why can't they be a fraction? All right, because if you examine them in their decimal form, all right, they're non-terminating, which means they don't stop, they go into infinity, but they also don't seem to have a pattern to them, as in the case of 0.333 forever and ever and ever. All right, they're both simultaneously non-terminating and non-repeating. All right, so that's why we have these symbols. All right, because the symbols represent the entirety of something that is infinite without having to try to, futile effort that it would be, writing what the number is, right? Think about pi, right? We're memorized for practical reasons. 3.14, right? When you're a little kid and they first tell you about pi, they say, oh, it's 3.14, but that's not true, right? That's just the front of pi, right? All right, it's 3.14159, whatever it is, into infinity, right? And there are people who compete in competitions, all right, that have it memorized to, many, many places. I had a friend, Dave Fiore. He won a contest to that effect. I think he knew it to at least 100 places, something like that. Anyhow, it would be practical to know that much of pi, but just understand also that that's just the front of it, right? Irrational numbers are non-terminating and non-repeating. Square root of 2, all right, is similarly is 1.41, something after that. And then there's this number that you will see, all right, e, all right, 2.71 something after the fact. 7172, 8182, something like that. Anyhow, they're famous, right? They are truly the superstars of math, right? Why? Because they meet these characteristics, right? Now, one thing that's interesting as well, I want to add to this, is these things have grown up with us. Humans, right? Where do they come from? Well, probably pi and the square root of 2 are the oldest of them, right, in the timeline of human history. All right? I'm going to put these numbers back, sorry. 3.14, 1.41, 2.71. All right? These, being the oldest, these come from the oldest form of math. Well, the oldest form of math is probably arithmetic, but the second oldest form of math, which is geometry. This is ancient math, if you will. All right. The square root of a negative, awareness of that, right, is a little bit more recent. This is from algebra. Which, by comparison, to periods of history, this would be medieval math, if you will. Right? And then there's the baby. All right, E. All right, the subject for this class. Right? This is the most recent in history. E is not from geometry, not from algebra, truly mathy subjects, if you will. All right, this is from finance. In terms of human history, this is what you might refer to as modernity. What does that mean? It means from the 1600s forward. So modern math, if you will. Right? And it is the foundation of calculus, right? At least if you taught it that way. Down below on the same piece of paper, there's famously Euler's equation, which is an awesome thing to behold, really, right? Whether you're interested in the subject or not, right? Why so? Because it incorporates so many of these important, famous numbers, right? The superstars, right? Maybe it isn't practical. We haven't found, at least I'm not aware of, a practical usage of Euler's equation, but it's elegant for its simplicity and the fact that it incorporates so many simple things, all right? 0, what could be more basic than that? 1, what could be more basic than that? E, I, and pi. Right? This is what they produce. All right, now as how to arrive at the number, all right, E, I'll just show you really quickly.
All right, here's a worksheet that I normally go through with people. Right. As I said, it comes from finance. Right. There is a simplified version of compound interest formula. All right. So just like other brute force techniques, right? For calculating something, you can produce ordered pairs, an x and a y essentially, by putting in whatever x's that you like into some function, all right? Following the order of operations because you're just sticking with the right side of the function. And calculate. So you're going to compound, this is what would be a version of compound interest formula. Right? What you would see without driving you crazy is that if you put 1 in here where there's an x and then as an exponent, all right, it would ultimately be 1 plus 1, which is 2. 2 to the first, all right, is just 2. All right, and so that first number as a result of doing this would just give you the coordinates 1 comma 2. If on the other hand you put 2 in here and then square it, all right, it would be 1.5, all right, 1.5 squared would give you 2.25, right? And if you proceed in doing this, what you will begin to notice after a while is that it's approaching a number, all right, just like pi, all right, comes from geometry, basically the attempt at dividing the circumference by the diameter of a circle. You notice that no matter what size circle, that you keep getting close to this figure, 1.31, 3.14. All right. Well, in the compound interest formula, if you keep putting these these values, you eventually get to this figure, 2.7181, 45927, whatever it is. You could verify if you'd like. All right. But that's the number that you get close to. All right. 2.71 something. All right. I'm just using the first 2 digits, of course. All right. Between here and there, you keep the 2, and then you get a little bit bigger. All right. Keep the 2, you get a little bit bigger. Keep the 2 a little bit bigger, and eventually it starts to lock in, an extra decimal place, and you go, that's 7 again. All right. Like an example, if you put in 1,000, what you will see is 2.7. All right. 169 something. All right. Just before that, 2.70, you get closer and closer and closer to it, right? The graph that is underneath here, all right, if you took the time and you put in these values, you would observe the exponential curve, right? So, just like every other exponential curve, right, at least those without some coefficient up in the front, all right, you go through 0, 1, right? And then, just because it's interesting, over at the point of 1, when your base is e, is 2.71, something like that. Might be a little sharper, all right, of a curve. In some instances, when you have a different exponential function, a little bit flatter, but it still behaves this way, Rapid growth, all right, non-linear growth, exponential growth, all right. This is using e as the base, right, rather than some other number. Let me show you this. There's a summary of different applications for exponential growth and decay. And then maybe do a word problem together. In general, if you have growth, a curve upward into quadrant 1. If you have a decay, you have a curve downward into quadrant 1. There should be an arrow like this here and like this here. Some applications of non-linear, meaning not x, y, just only,
rapid growth or decay are these four types, right? Population growth can be calculated with this formula. Compound interest, a version of it, calculated with this formula. Mass of a radioactive substance, right, which is cool in physics. And then something called continuous growth or decay, right? Now, the labels you may notice are changed, right? But don't let that deter you, right? Let me zoom in on the compound interest here. And the population, right? To call something P of T is just in lieu of saying Y, right? And to have T as the input is to use that instead of X, right? In this case, the starting point, which has a subscript of naught, all right, P naught, 0, initial, whatever you like, starting, all right, that's what would normally be the A value to it, you know, from the earlier incarnation of this, something like that. So I try to list that here, all right? If in this formula they're opting for capital P with a subscript, all right, that's the initial population for the population formula, the starting value, all right? On a graph, it would be the y-intercept by another name, all right? Instead of an X input, they just call it T because we're referring to time, but the time has to be in years, all right? R that shows up in this formula is actually a percentage, which means that if you're gonna incorporate it in a practical way, you're either gonna have to convert it to a decimal, which is probably more likely, or a fraction, all right? Especially when it comes to money, right? Because money is decimal, right? When you get a percentage, just use the decimal equivalent of whatever the percent is. So say hypothetically you had 5%, as a decimal it's 0.05, all right? And in this case, for the compound interest, there's an extra feature here. N is the number of times compounded in a year, right? What does it mean to be compounded? That's important, so let me just write that here for reference. When it comes to something called compounding, essentially, it's when interest is calculated, from an accumulated value. Right. Rather than just an original value. So that's basically a calculation is performed, you get a result, and then you put that answer back into the formula, all right? It's compounded. Interest, is, in the case of compounded interest, is when interest is calculated from an accumulated value rather than just the original value one time, all right? All right. Just to go through the motions here, all right, if you scoot over to the other two, there's amount of mass of a radioactive substance as a function of time. All right, again, the labels have been changed. A is in amount of mass, all right, as a function of time, A of T. A naught is the original mass amount, right? So again, on a graph, it would still nonetheless be the y-intercept in math world, all right? T is time in years. In this case, it's a little bit less complicated. There's something called half-life in physics. This is the time it takes for mass to reduce by half of the original amount, all right? Since it's a time, it's appropriate to make this as part of a ratio of time, all right? Years in relation to the half-life, right? The standard of which something decays, you know, unique to the substance, because it's different depending upon if it's uranium or plutonium or what have you, all right? Then there's this, a slightly more sophisticated form of sort of continuous compounding, A of T, all right? Sorry for the schmutz here. A is the initial value nonetheless, all right? Again, we went with the more traditional label perhaps, or starting point. T is still time in years. And then E is incorporated as the base in this case, right? The base in this case, right? The R value that you see here is still a percentage again, which means you probably, if you're talking about money, you're going to put it as a decimal. All right. All right. Let's do another word problem. And keep it trucking along here. This is the other page in the packet of word problems. Seems too much. Okay. I'm going to read this. All right. You invest $12,000 at an annual rate of 3%. Find the balance of the account after 5 years for each type of compounding, quarterly, monthly, or continuously. I need a little bit of light, so I'm going to pull this back. And I'll zoom in on this. So here's an example of compounding. So we'll use this formula at least to begin with. Right? The account value as a function of time is equal to A naught or P naught, it doesn't matter. The principal is usually what they use for P. Times 1 plus R over N times NT. Okay. All right. Why use the letter P? P stands for principal, which I believe is spelled AL in this case. I don't remember that. It's the initial amount. The initial dollar value of something invested or borrowed. All right, now in this case it's $12,000, which means that you're definitely going to put 12 grand in here in place of P naught. All right. When it comes to these other things, quarterly and monthly and continuously, right? These are the degrees of how often compounded. If the N value that you see here is number of times compounded, right? It's going to be different for each of these, right? Just scoot this up just a little bit, or maybe just make that smaller. In the case of quarterly in a kind of vague way is saying that you're compounding 4 times a year. So you're going to put a 4 there in that instance, all right? If it's monthly, again, in a vague way, that's saying that you're going to compound 12 times a year, all right? And if something is continuous, what that means is that you're going to need a different formula at that point, the continuous formula, all right? But we could do this using this one for quarterly and monthly, all right? So we're going to find the balance of the A's account as a function of time. After 5 years, so technically a 5 would sit there, and the same thing here. But with these values inserted, $12,000 in each of these cases, and then the more interesting guts here. 1 plus something over 4, 1 plus something over 12, and then 4 times 5, and then 12 times 5 here. The only thing that I've left out is the actual percentage rating for the investment, which is 3%. Now again, if it's a percentage, remember that that's 0.03,
Right, so it's 2 decimal places scooted over to the left.
So you would put 0.03 here, and the same thing here, 0.03 here.
All right, that's the only difference between these. All right, the number that you stick here, and consequently here, the n values, the number of times compounded, would be 4 in the first case and 12 in the second case. All right. The way that this works out is that an investment in this scenario would be something like $13,934 and maybe 21 cents if it's rounded to the hundredths place. And in this case, if it was compounded 12 times a year, $13,939.40. And so you can see that compounding obviously is going to give the person a greater return on their investment. Right? Don't you wish you had that much control of your bank account? I know I do. Please compound my 5 cents, you know, 1 billion times. Now, insofar as the continuous portion of this, it's going to be the alternative formula, which means that you'll be using this instead. Starting with this, the function is the account value as a function of time. Times A, using E is the base number, because E is so cool, and then R times T is the input. All right. Much of the same features, all right, just different labels. All right. What is the initial value? Instead of calling it a principal, it's just what the account has, I suppose you could say. 12,000 would still go there. All right. The percentage would still be 0.03 as a decimal, and the time would still be 5. Right? So if you plug this into your calculator, very carefully, of course, right? Or you follow the order operations by hand, which is also respectable, what you would get for continuously compounded investment would be something like $13,942.01. So ever increasingly, it is to one's advantage to compound interest. Right. Just realize it's a different formula. All right. Now, insofar as section 6.2 and 6.4, the transformation, I'm just going to flash this. This is what is relevant from both of those. I'm going to zoom in on something, just bear with me. This is as concise a summary as one could get, and the effects. All right. If you have an exponential parent function, toolkit, whatever you want to call it, this is exponential function. Most basic would be a base to input. All right. In the transformation model, it would look like that. Right? Right. Here is a slightly amped up version of it where there's a constant up in the front. So maybe that one's better actually. All right. It has the usual features. Right. The horizontal and vertical shift are controlled, instead of calling it H and K, they're called C and D. Notice that the horizontal shift is part inside the function, all right? And the vertical is technically outside the function because it's plus something, all right? Then there are stretches and compressions, all right, which is controlled by the coefficient up in the front. There's a stretch depending upon the absolute value being greater than 1, and a compression based upon the absolute value being somewhere between 1 and 0. So a fraction essentially. It will compress the graph. All right. Then there's reflections. Reflections about the x-axis, which means that it would be upside down. All right.
would be controlled by a negative coefficient up in the front, so negative a is -1. And for a reflection about the y-axis, it would be in the function here, right, which again produces a fraction itself. All right? When you have a negative exponent, you write that as a reciprocal. All right? When we get to log, which is section 6.3, right, here again is the transformation incarnation of it. This is logarithms, a logarithmic function, all right? And here is the transformation model, all right? All right, horizontal and vertical shifting controlled by those features, all right? Expect that stretches and compressions controlled by the coefficient A, the thing in front of the function. Technically it's on the outside, all right? Reflections are controlled by signs, all right, here and inside. Okay, that is, I said, I couldn't do it more justice than that. That is a very nice summary of that. All right. Now, to get to logarithms, let me turn off my projector and we'll get through that. I'm going to take this down for a moment. That's much brighter. And continue. Okay. All right, we have these two new functions essentially that we're discussing. And really we've been spending a lot of time with the first type, the exponential type. And now we're going to get to the inverse of that, which is the logarithmic type. Right. These, remember, are inverses. I'll come back to that. Now you might be wondering, especially as an English speaker, geez, where on earth did this word come from? All right, John Napier, if I'm pronouncing that correctly, was a Scottish mathematician, all right, from say the 1600s, something like that. He coined the phrase, right? Coined the term logarithm. Logarithmic. Right. It comes from Greek, actually. This is a Greek fusion of two words. Logos, which in this context is referring to a ratio, and arithmos, rather. Which is numbers. All right, a ratio of numbers. Now, it has some similarity to a fraction, right? In the case of a fraction, this is stretching a bit the context here, but in the case of an ordinary fraction, right, there's a number, right, literally on top of another number. And in essence, on top of is the context of the phrase logarithm. There is something that is on top of something else in the way that you write it, but it's not a fraction or a ratio in the classic sense of a fraction, right? It's just that is written atop something else. Right? It's just not referring to a fraction per se when you say ratio. All right. I think, to me, not to be disrespectful, but as a person of Scottish ancestry, right, I just find that kind of funny. Lager, it just sounds like somebody was drinking. Like I can't even get a decent logarithm. Anyhow, let's compare the shapes here using familiar things. Y is b to the x, right? The exponential model, right? And if we wanted to make this true to form function, we put it in function notation, and this would be as much of an alteration, right? Just opting for italicized f of x instead of y, right? Being that logarithms are an inverse of exponential functions, that shifts the position of the x's and the y's, essentially. Right? So what you would have, and you're not likely to see it, is that this would be x to the base of y. Right? When you see the more familiar incarnation of this, it's rearranged from the perspective of y, but it still means this. All right? I think my table might be in the way. But what I'm saying here is, if we were to take this, x equals b to the y, and rearranged it so that it is in more or less the normal perspective, from the perspective of y, right? What you have to do to account for that, to acknowledge that, is you write the word, logarithm, essentially, the abbreviation for it. So you would see y is equal to, I'm going to put this in black because I think it'll be easy to see. Y is log of x with a little b in here, right? That's where there is a sort of fraction, that is to say something above something else, ratio, all right? The word log of x is above the base, right? Okay. Anyhow, this, even though it doesn't look the same, means this. Right. And then again, if you wanted to go the whole 9 yards, you would opt to the function notation. So instead of saying y, you would say function of x is equal to that. All right. Okay. Now, how would you say it? Right. When you're reading it out loud in English, you might say log base b of x is y. Right? Is, remember, the mathematical equivalent of that. The symbol is just the equal sign. Okay. So log base b of x, because it's presented in the style of an argument, like in function notation, parentheses, right? Is equals y. Okay. Log base b of x is y. Okay. Just understand this is what it really means. That's just how it looks. I guess just for the familiar arrangement. Again, it's from the perspective of y that this is arranged. Yeah. Okay. Logarithms, they sound like beer. All right. All right. Now, I'm going to show you the peculiar way that I handle these, right? Which is, it's functional. It's It's not wrong. It's just maybe a little idiosyncratic. Anyhow, I think it works nicely, you know. Gladly share it with you. I made this handout to summarize. And I have to dim the lights in here again. Put this back. There's a couple of things that you'll be dealing with, especially in the section 6.3. Converting from one form to the other, as you can, they're inverses, right? Forward and backward, and then actually evaluating them. So this is what I mean by the peculiar way that I sort of deal with these, right? It's not wrong, it's just, again, idiosyncratic, I guess, right? If I had to explain to a person who has never seen any of this stuff, how do you convert from something in the logarithmic form, what you see here, to the exponential form, which is maybe the more warm, fuzzy, and familiar way of doing it. I draw a jelly bean, right? Literally, every time that I do this, right? And then, although it is a peculiar way, again, of saying this, I admit, I read the jelly bean counterclockwise. Now, say that to another person, whether they're in the field of mathematics or outside, especially, would be even worse, right? You go like, I read the jelly bean, all right? They could be like, yeah, whatever, you know, get the straitjacket, you know. But I do, I really do, all right? And then I set the bean to the argument. Remember, arguments are things that are written in parentheses, all right? So here's a couple of examples just to prove that I'm not really crazy. It's not in an obvious way. I do enjoy this. I need a little bit of light. Suppose that you had this, log base 3 of the argument 9 is 2, right? Remember, is a stand-in for equals, right? Log base 3 of 9 is 2, right? You might read it like that. If I take my own medicine here, if I follow my own weirdo procedure, I'm going to draw a jelly bean, all right? Or what I think of looks like a jelly bean, right? Which is like this. All right, you could argue it looks more like a hot dog or a potato, but whatever, it's cute, right? Why do I do that? Because I'm trying to sort of give myself a visual cue, all right? And again, I read it sort of counterclockwise, right, which is that orientation. Seeing this first, I write that first. Seeing this second, because I'm reading counterclockwise, I write that second. And then I set the bean, put those features there, all right, equal to whatever is in the argument. So in this case, it happens to be 9, all right? And tell me that that's wrong, all right? Is 3 squared equal to 9? It is, right? So jelly bean logic is fine, okay? Here's another one, all right? All right. I've been waiting for months to share this with somebody. Here's an uglier one, right? If you had the log base 6 of the argument, square root of 6, just coincidentally, is 1/2, all right? Here, I'll do a different color jelly bean, all right? Losing my mind. I encapsulate these features, all right? And I read it counterclockwise. That's the first thing that you would, the bottom, all right, naturally. And then this is the second thing, 1/2. Right, is the exponent in this case, and then set the bean, as weird as that is, equal to whatever's in the argument, which is square root of 6. Right? Now, again, is that untrue? I don't think so, because this is rational notation for what would be radical notation, right? 6 to the 1/2 exponent is the square root of 6, right? Nobody bothers to put a 2 in here in the index or 1 there because it's superfluous, but that's what that would translate to, right? So again, it seems to work, right? My weirdo sort of jelly bean drawing, all right? Now, it's less elegant, all right, arguably, when you're going the other way, all right? but there's a procedure to it as well. I'll show you. Perhaps I should have done this to begin with. These sort of calipers that I've drawn here, right? Again, this is something already beginning in logarithmic style, more or less as a general form. I chose the letters B for base, because I think that's intuitive, C for constant, not that it has to be, and A for argument. All right, that's just logical to me. Here's my jelly bean to encapsulate the base and what would be the constant over here. Why? Because that's the base and that becomes the exponent, and the argument is what it's set equal to. All right. This is basically the end result. B to the C is A. All right. On the flip side, all right, if you're talking about exponential to logarithmic form, all right, you have to start by writing the word log. All right. So it doesn't have to be capital L, but whatever. You set log, all right, equal to whatever the exponent is. So if you see something that is in exponential form, and it will be obvious because there's a superscript number here, or variable, all right, and then you would just write this immediately. Log space is whatever the exponent is, all right? Then the opposite side of the equals here, all right, will become the argument of the log function, okay? A is an argument. And then one thing that you could take, sort of as a security blanket, all right? The base is always the base. So if it's the base here, make it a base there, all right? Just make it the bottom of something, all right? The base is always a bottom, somehow, all right? Why? This is a logarithm. It's a ratio of numbers, somehow, just not a fraction per se, all right? Let's do a couple of examples. All right, suppose you had 2 to the third equals 8. Now, very clearly, this is of the exponential form. All right, if you want to write this in logarithmic form, all right, start with writing the word log. I'm afraid to use green, but I'm going to try just for the sake of consistency. All right, log, little space, and then you set it equal to whatever the exponent is. If the exponent is 3, log something is 3. All right, then the opposite side of the equals, all right, will be the argument. So you would put an 8 in here, in this case. All right, and then what was the base to begin with will be the base to end with. So if it's 2, then it's a little 2 in here. So log base 2 of 8 is 3. Right? That makes sense, right? Because 2 to the third would be, in fact, 8 if you did the multiplication. All right. Here's another one. 5 to the third is 125. Right? Start by writing the word log, just because I'm superimposing it on my scribble here. I'm just going to write it like this. Write log, a little space, is the exponent. So if the exponent is coincidentally 3, you put equals 3 here. All right. The opposite side of the equals will become the argument. So you can put that in parentheses. A lot of times in textbooks they don't bother to do that, but if it's a function, why not, right? I think that makes it more obvious that that is, the input typically. Then what was the base 5 remains the base. It's the bottom of this thing. All right. One more of these. So if you had 2 to the negative 1/2, 2 to the negative first is equal to 1/2. All right, which is true. In the logarithmic style, you write the log is equal to the exponent. So it's -1. The opposite side is the argument, 1/2. What was a base continues to be a base. Right? Okay. All right. Now, the bottom of this is the situation where you have to evaluate. when evaluating, you set given logs equal to a letter, right? Now, a lot of times when they just give it to you, it's more or less an expression. It's not an equation. You make it an equation, all right? You make it look like one at least, right? So whatever is given, log something or other, do this, all right? Do yourself a favor. Set it equal to a letter, all right? Since in theory it's supposed to be an inverse, I like to use Y's. You don't have to. You could use any letter that you want. I think oftentimes textbooks will simply opt for X anyway. All right. Then you convert it to exponential form. All right. And in many cases, all right, because we're not at section 6.5 or 6.6 yet, you could just simply infer what the letter ought to be. All right. There are techniques for figuring it out. Right, but we're not really there yet, so we're just kind of getting our feet wet. Right, so you will try to reason it through. You can infer what the letter ought to be by comparing the two sides, especially if they're the same bases. Right. Let's do some examples. All right. I'm going to turn this off because it's unnecessary now. And see what I can get away with doing here. Okay, so here's some examples of evaluating. Were you to evaluate log of base 4, log base 4 of 64. All right, that's how it will be given to you more or less in the style of an expression. Again, I would disguise it as an equation, right? If you change it to just this much, if you go, all right, keep all the same features, but I'm gonna add a letter, I'll put Y here, okay? Then what you would do is convert this now to exponential form, which is, again, draw the jelly bean if you like that weirdo style of doing it like me. Reading it counterclockwise. The 4 you read first, the Y you read second, the argument becomes what it is equal to, so 64. All right. Now, you'll probably be given problems that, again, you could easily figure them out, all right? These numbers are going to work well together. Right? If you know your multiplication tables at least up to 10, right? You know that 40 is what 4 times 10 would be. 4 times 4 is 16. 4 times 4 times 4 is what? 16 times 4, which is 64. There you go. So 4 cubed, right? Y would have to equal 3. Okay. You have to basically, on a case-by-case basis, try to figure out from the fundamental knowledge that you have what this would make it true, or how it would make it true. All right. Here's another. There are techniques forthcoming, but it's a different section, so I'm trying to bite my tongue a little bit. All right, suppose we're going to evaluate log base 3 of 1/27. All right, again, it's not written in the style of an equation, but make it so. All the same features, but with the added benefit of a letter. Right? Some letter doesn't have to be Y. I just like Y's. Encapsulate the pieces that you would. 3 to the X is 1/27. Okay. Now, on one side, to reason this through, you have a whole number. On the opposite side, you have a fraction. So remembering that if you have a negative number as an exponent, this causes things to be a reciprocal. So the first thing that you might reason if you have a fraction here is that this would have to be a negative. All right, now as far as the number 27 is concerned, try to think of the relationship you're aware of between 3 and 27. Again, if you know your multiplication tables of 3, you know that 3 times 9 at least is 27. All right, but it just so happens, all right, that 3 times 3, i.e. 3 squared, is 9. All right, so 3 times 3 times 3, i.e. 9 times 3 is what it is. It's just a 3 again, coincidentally. It's just a negative 3. All right, so x in this case is negative 3. Okay. One more of these and then I'm going to shift gears. Suppose you had log base 5 of the cube root of 5. All right, again, I would fill in some features, put a letter in here somehow, make that perhaps equal to x. If that makes you more comfortable. I like x's, but technically would be a y, right? 5 to the x, therefore, would be the cube root of 5, right? Now notice something. If you have the radicand is the same number as the base here, remember that the alternative way of writing something in radical notation is to put it in rational notation. It means the same thing, but this would be 5 to the index of 3 with a 1 for the exponent. And in this case, this is what's interesting. All right, these are the same bases. So if they're the same bases, what would have to be true about the exponents? They would have to be equal. So in this case, x is 1/3. Okay. All right. Now let me give you, I think it is the last sheet for today, and then I'll stop. What time is it? Oh boy. 12:15. We're nearing the end here. All right. Wake up here. Alright, here are the two special types of logarithms summarized. Okay. There are the logarithms that have a base 10 in them, and then there are the logarithms that incorporate base e, right? They're known as the common log and the natural log. On your calculator, it is likely, if you tinkered with it, you may have noticed these buttons. All right. The button on your calculator that simply says log, all right, is referring to a base 10 log, meaning you don't have to bother typing it. All right. There's a second button on your calculator that is usually just LN, all right, for natural log. That is, again, when you have a base E. So if you press this button, you want something that has a base E specifically, okay? Now you may notice that there isn't immediately a button that is for other types of bases, but historically there used to be a formula, which is at the bottom of this piece of paper, the change of base formula, that would allow you to use either of these buttons to evaluate something. All right. More recently, the software has been adapted to make it a little bit more intuitive, so you don't really need the change of base formula, but it's still a handy thing to have. All right.
Now if you take a look at these, this is how things unfurl, all right?
If the base is always the base, and it is, whether it's in exponential form or in logarithmic form, all right? To have something written this way, base 10 to the y is x, from the perspective of y, acknowledging that this is the arrangement, log equals the exponent, the base is always the base, the opposite side is the argument. This is how you would actually write it if you were going to be very explicit about what the base is. Oftentimes, because it is the common log, nobody bothers to put the 10 there. It's just understood, right? It's the same situation, more or less, as you leave out positives if it's a convenience for you. You leave out zeros if it's a convenience for you. You leave out decimal points if it's a convenience, or ones, right? So this is more likely the way that you're going to see it. All right? Just realize that that's really what it means most explicitly. All right? In a similar way, base e, all right? That would be the log set equal to its exponent, right? The base is always the base and the argument is x, the opposite side, all right? You could write it that way and you'd be totally correct, but it's not likely to be written that way. It's more likely you'll see it like this, all right? The natural log. It is understood that this means this, okay? All right, now again, historically, if you wanted to evaluate some logarithm that was neither of these two bases, something other than 10 or e, right? What you could have done is incorporate something called the change of base formula, right? And it is this. It turns out that if you had some unique logarithm, I'm just going to throw some numbers in here. Suppose you had a log of base 5 and of the number 2. And you wanted to know, you wanted some more or less satisfying number to evaluate that, right? Remember what this would really mean, right? It would be what's the exponent if you have that, all right? This would be determining x, all right, if 5 is the base and 2 is the outcome, all right? The old-fashioned technique with your calculator, at least, was to go, all right, I'm going to use the change of base formula. Normally what that means is that somebody would just press the log button on their calculator here and it would automatically be base 10 without having to acknowledge that. And then consistently doing that down here as well. As long as the bases are the same, all right, you could get away with just entering this ratio, right? Just take what the base number is and put it in the argument here, and take what the argument is here and put it on top, all right? You could, if you wanted to, use the natural log instead, right? Because then they would be base e and base e. There's just the trick to this, is often the case with math, is consistency, all right? Anyhow, let me show you what happens as a result. All right. If you take a calculator and you incorporate the change of base formula, right, to figure out what log base 5 of 2 would be, all right? You would press, where's that button? Over here. Log 2 divided by log 5, all right? You would go, all right, I'm just going to use common log over common log, all right? But in this arrangement, the 2 on top and the 5 on bottom, because that's what the formula would tell you, all right? And you'd see what that x value would be. Hit the equals dopey. Not that. 2. This is what happens when you do things backwards. You get this decimal, right? All right, 0.43, whatever it is. All right, just for the sake of saving it. All right, x should be something of 0.43, whatever. All right. Since the software has been updated, there's a couple of ways you can do without the change of base formula, though it's still cool. All right. If you press second and then alpha, you're engaging these green function keys. So it's the second one you want, second alpha window, and you see that you have log base formula right there. So if you choose option 5,
it allows you to intuitively enter the base of your choice and the argument of your choice. So I'm going to put 5 where there's a space, and I'm going to put 2 where there's a space. All right, and it should give me the same answer. All right, 0.43 is expected, right? All right, that's cool. All right, there is another way to get to it. All right, if you go through, I want to say it's the math button, and probably, if it's not the bottom of this list, yeah, it is the bottom of this list. You see log base again, it's the same function. And you can intuitively put 5 and 2 there. All right, 5, 2, and scoot on out, and then hit enter, 0.43. It's still nonetheless cool, all right? If you use the change of base formula with log base e, all right, put a 2 in here, encapsulate, divide, hit natural log again, put 5, close it, and then hit enter, you get the same answer, okay? I think that's it. Yep. All right. That's 4 sections. All right. More likely you're gonna have homework from 6.1 and 6.3, I believe. Okay. All right. This video was for Wednesday. I will see you again on Thursday. All right. Be careful out there.